Microchip, INFRACHIP, for giving me this opportunity to present my work, which is on brain-inspired neuromorphic computing using two-dimensional materials. So when I joined Chalmers last year, so I noticed that people are very much enthusiastic about the word neuromorphic. So let's start with that. So as you know, because I didn't attend the previous talks because I was in the conference. So, but basically, many of you know what is neuromorphic. So let me just tell you in 2 words. So neuro means to do with neurons, and structure, morphic means structure or form. So this word is actually proposed by an emeritus professor in Caltech, whose name is Carver Mead. He's also known as father of neuromorphic engineering. And it is a field that mimic the structure and function of the human brain. So from the very young age, a child can point at different animals, such as cat, dog, or squirrel, and confidently say that whether it's same kind of animal or not. But he might get it eventually wrong sometimes, but fairly soon he learns to make it correct. And like inside his head, after encountering few examples of each type of animals, he even can learn these things without knowing, without seeing any kind of diagram of any animal or knowing the any kind of species, whether it is a mammal or something. So similarly, like this, people can learn to recognize a cat or understand a word, and also like to enter a room and notice that something has changed depending on their by observing the surroundings. So this is the preliminary stage of human learning and also human intelligence. So the next question is, can machines have such kind of intelligence? The answer is yes. Thanks to these 2 Nobel laureates, John Hopfield and Geoffrey Hinton, whose inventions made it possible so that the machines can have this intelligence similar to the human brain, which is nowadays known as artificial intelligence or AI. The development of AI is basically has exploded over the last 10 to 15 years, and it is based on a structure which is known as artificial neural network. And the network that Hopfield built consists of the nodes, like here the black or white. The black indicates, let's say, 0, or white indicates 1. So these kind of nodes are connected via joined via different strength of connections. So when an image is being fed to these nodes, which are the values of 0 or 1, the network's connection are getting adjusted based on the fundamental principles of physics and methods derived from the spin, and such that the saved energy, the saved image has the lowest energy. So this kind of neural network can be also analogous to a rolling ball, like rolling a ball through a landscape of peaks and valleys. So it's like when a image input pattern is fed to the network, which is closed to one of the saved memory. So finally, like this ball, it comes down to the at the bottom of the energy landscape, so that which is basically similar to the repeating the closest saved pattern in its memory. So because of these kind of developments, so nowadays artificial intelligence makes our daily life easier. And for an example, like some of the examples are self-driving cars, smart assistants, spam filters that you get on your mail automatically goes to the spam similarly. And I hope many of you know about this first social humanoid robot, Sophia, made by a Hong Kong-based company in 2016. And of course, many high-end electronic industries have their own AI tools, such as Samsung has Bixby, Amazon and Alexa, and Apple has Siri, and so on. But the problem is the problem is the power consumption. So, like in this current AI tools, the problem is they consume a lot of power. So basically, this kind of like these two powers generate from two different regions. So one is digital computing. Like there are two different origins. So in case of digital computing, there are two states known as one is binary, and sorry, one is zero and one is like one. So when the bulb is at the bulb is at completely off state, so it's a zero. So it's an on state, so it's a one. But what happens when I give a task to turn this bulb on at 50%? So you need definitely two switches. One is off and one is on. So accordingly, different kind of more number of switches are required to generate more number of tasks. So basically, similarly, in a microprocessor such as Intel, it has a like nano transistors that acts as a switches, and these nano transistors arranged in such a way that, like in a binary computation algorithm, so that like if we want to like show a number 25, so it will arrange like this. So basically the message is that like in case of a digital computation, it will require to solve more complex problem, it will require more complex architecture. But at the same time, in case of an analog computing, if you use a single switch, it can give you different, like can generate different kinds of illuminations according to your like requirement. So this is based on, this is the benefit of analog computing. So you can switch it to different states. So there is an also interesting experiment like in 1997, where IBM's Deep Blue computer beat the world champion Gary Kasparov. So in this experiment, what they observed is that, of course, Deep Blue has a capacity of imagining 200 million chess positions per second, but so it's a tough challenge for Gary to win this match. So, but when you look at the power consumption aspect, Gary used only 20 watt, like Gary's brain used only 20 watt of power, but Deep Blue supercomputer used orders of megawatt of power. So this is the reason. And the another and when you go to the inside the human brain, which works as an analog computing, so it has a 10 to the power 11 neurons and 10 to the power 15 synapses, which are connected in a parallel architecture, and for each operation they use only 20 watt of power. But when you compare it with a supercomputer such as Blue Gene, so it has only 10 to the power 4 neurons and 10 to the power 11 synapses. And this is based on a von Neumann architecture. So this is, and this von Neumann architecture, even it is even slower than mouse cortex. So basically, when you look inside a computer, you will see a CPU somewhere here and memory somewhere here. So this CPU and memory is physically separated by a 4 centimeter. And when in case of this, in this architecture, when during the computation, data goes from the CPU to memory, flows from this to, and which like increases the significant energy consumption, which is known as the memory bottleneck. And because of this like memory bottleneck, uh, like this when we compare human brain in terms of speed and power, so you will find that human brain is much more ahead than the current existing hardware, such as application specific integrated circuit or field programmable gate array, and it only used 20 watt of power, and the speed is very high. So when you look inside a brain, so you will find a branch of neurons like this. And this is the real image of an entire neuron, which is taken at this Crinstiel Hansel lab. And this entire neuron is having a dimension of 200 micrometers. And if you zoom in between the two neurons, you will see something like that. And these two neurons and are not in physically connected. There is no physical connection. So they communicate each other via electrical or chemical signals. So as you go through life, your neurons inside your brains gets adjusted, which is known as plasticity. And if how does the plasticity works? So when you get a input signal like in the presynaptic neuron, so it will release the neurotransmitters, and the neurotransmitters goes to the receptor which is in the postsynaptic neuron and activates the receptor, so that there is a chemical imbalance occurs between this Na plus by the Na plus or calcium ions. So this chemical imbalance basically they trigger as a electrical stimuli in the postsynaptic neuron, and we generate postsynaptic potentials, which is known as this potentiation and depression. So when the strength is high, we call it as a potentiation. When the synaptic strength is low, then we call it a depression. So in this way, by modulation of this synaptic plasticity, we can generate multi-level analog memory instead of digital one. So the next question is how to replicate this kind of brain behavior in our current architecture. So this is the biological neural network which contains both neuron and synapse. So if how we can replicate them, so we need a new kind of architecture, which is basically we can call it as a crossbar architecture. So this is a parallel architecture and it can perform vector matrix multiplication, and each single device can able to generate multiple state. And by using a vector matrix multiplication, we can parallelly connect all the devices that we fabricate. So this kind of hardware can be used to communicate with the artificial neural network. So the next thing is that in the current technology, silicon, which is based on the silicon based CMOS technology. So the scaling down of the transistors has been we have seen that throughout the years, like in 2000s they are using planar FETs, and where 2010 they are using FinFETs, and it goes to get all around FET in 2020-22. Then in recent years, so people have also done 3D integration of these transistors to increase the number of density per microchip. But as we go towards the as we shrink down the transistors dimension, we are approaching a unit cell limit of the silicon, which is 0.6 nanometer. So the next question is then and if we fabricate using a short channel, using silicon transistors using short channel, because of this short channel effect, which is the hot carriers or velocity saturation we are getting. So what is the alternative? There comes the groundbreaking discovery of two-dimensional materials, which is first discovered the graphene by these two Nobel laureates, Andre Geim and Novoselov. So these kind of two-dimensional materials are possess unique crystal structure, which are having which is atomically thin, like angstrom level thickness. And because of this weak interlayer van der Waals bonding and strong interlayer covalent bonding, so it is very strong in two-dimensional but weak in three-dimensional, so we can easily peel out. So how to prepare? So there are two different kind of approach. One is top-down approach, which is the way the Nobel laureates used to exfoliate graphene. So they used this approach, like exfoliation of from the bulk crystal and to make thin layers. And another way is bottom-up approach, where you can chemically synthesize this kind of material layer by layer. So these are the images of different structures like hexagon, triangular, and also you can see this is a single layer and this is a bilayer, and bilayer with different orientation. So this kind of things you can do using chemical vapor deposition techniques. So, and what we do after if we grow or exfoliate two-dimensional material, then we fabricate the device on these materials. So this kind of devices are fabricated on a dielectric layer on the doped silicon, which is act as a gate dielectric, and we deposit this top electrode as a drain source contact by using photolithography process. So this kind of 2D material based devices has like if we look at the Moore's law scaling, so they are the next generation devices that can extend beyond the CMOS scaling, and many different functionalities can be realized like quantum technology, neuromorphic, photonic circuit, and so on. So these are the future. So then how to generate like artificial synapse using this two-dimensional material. So basically we'll use different resistance states by using different stimuli, by external stimuli using two-dimensional materials to replicate biological synaptic behavior. So today I'm going to discuss about like three different like works of our group. Like one is a light-driven external stimuli to generate as a artificial synapse. One is charge-driven, and third one is ion-driven. So basically, as you know, monolayer MOS2 these kind of materials are direct bandgap materials. So if you shine and the wavelength and the bandgap of these materials lies in the visible range, visible light range. So if you shine a visible light, which is red, green, or blue, so you can excite, you can generate multiple states, memory resistance states of this material. So these are the like three different wavelengths, which is red, green, and blue. So you can see the like by changing the power or exposure time or the wavelength, we can tune different resistance or explore different resistance states of this kind of a material. So this can be treated as a multi-bit states, and these are kind of a like memory behavior, which can be regarded as a synaptic weight. And these are some basic synaptic behavior that we generally use to like validate our device, whether our device can work as a artificial synaptic device or not. So one of the properties is you can call it as a pair pulse facilitation. So it is a short-term event-driven like plasticity, where the current in the postsynaptic neuron depends on the temporal correlation between the pulse pair incident on the presynaptic neuron. So if the temporal, like the time difference between these two pulse pair increases, then the current in the postsynaptic neuron decreases. So this is the behavior of PPF with interval of time. So like it replicates similar to the biological neuron behavior. So if the time difference between them increases, then the like second postsynaptic current decreases. And another behavior is like there is a most like one of the famous learning technique is Pavlov's associative learning technique. So, and this is also used to like mimic the learning and forgetting behavior of a human brain. So how is this work? So you have a like two event, let's say arrival of food and a ringing of bell. So generally arrival of food, makes dogs to salivate, but ringing of bell doesn't make the dog to salivate. But if you do this like events at the same time, then the dog will salivate because of the food. And if you do like continue to do this for several days or something like that, then the dog will of course salivate, because this is the training of dog that ringing the bell and arrival of the food means that it will salivate. But after the training, if you only ring the bell, uh, it will salivate, because it will assume that the food is coming. But after some time, it will not salivate, like it will forget, okay, the food is like ringing the bell means doesn't mean that the food will come. So we can replicate this kind of behavior using this optoelectronic artificial synapse in our device by using two different wavelengths of light. So let's say this blue light pulses that we use. This is the first event, which is the arrival of food, and the red light pulses, which is the second event, which is the ringing the bell. So, and we like, let's assume there is a threshold current, which is 15 nanoamp, let's say here. So if we do the threshold current, so you can see like if the current increases beyond the threshold current, then it means the dog will salivate. So similarly, you can see like in the like at the same time, if we do both the events back to back, then it is reaching the threshold. That means the dog is salivating. And as you continuously do on like the training of the dog, uh, like continuously giving the two inputs like the red light pulses or blue light pulses, then we are increasing the synaptic strength of the dog's memory, so it will salivate. But if you stop giving a blue light pulse, then it will continuously like going to decay the conductance states, and after some time, after some repetition, it will forget to salivate. So this is a behavior that we can also like um, learning and forgetting, this kind of learning forget we can replicate using our device. So like there is another kind of device where we don't use any lights, only we can use only like electronic signals to generate this kind of potentiation and diffraction behaviors. So here we actually make like this 2D materials into like we shrink the 2D materials by fabricating like by processing it after like dry etching and wet etching. So this is a crystallographic oriented anisotropic wet etching. So after the wet etching, we can go beyond 10 nanometer narrow 2D materials, and in this kind of 2D materials, so the edge to surface ratio is very high. So because of that, so whatever current you will pass through these 2D materials, so it will activate the electrons will, or the charge carriers will go to the trap states, and these trap states holds the electrons, which is basically the basis of memory we can get. So by using this architecture, if I like do the IV measurements, so you can see the like set and reset, which is the memristive operation, but it is not a digital kind of memory that people show in oxide based memristors. And also like this kind of structure is a mem transistor structure. So there is a one more modulatory neuron which through which we can like control the different like synaptic current range. So this modulatory neuron is basically our gate bias. So you see like this is the like 500 pulse cycles, like, and if you change the gate bias from 0 voltage to 60 voltage, you can change the different conductance regime, and it is quite stable. And so this is the performance of a MEM transistor. And also this kind of like nanoribbons can give you like different synaptic operations such as long-term memory and short-term memory. So if you increase a number of pulses, so and then you just relax it, and then you see the after the relaxation. So in after the number of, for the case where the number of pulses is high, the relaxation is not going to its original state. So it's like it has some memory. So we call it as a long-term memory. But if we use short number of pulses, so you will see like after you like stop the giving the pulses, so in the relaxation, it will go to the zero state, zero conductance state. So, and similar behavior you can also get from a frequency dependent, like the here frequency means the time difference between two pulses. So that also, like that is the temporal correlation I was talking about, like this PPF behavior. So by also you can see the long term and short term, you can vary the memory from long term to short term memory as we see in our brain. So it is basically like if we like meet a person for a one time or two time, so basically we'll forget after one month. But if you meet a person every day, then you will generally not forget his face or name. So this is the similar behavior. And also we can tune this potentiation depression using different pulse width and different pulse numbers. And lastly, I would talk about this ion-based artificial synaptic device. So here we have used a CVD grown WS2, which is a triangular WS2, and this is a monolayer. And we used like AG as a source drain contact. And here you can see like, and during the CVD growth deposition, we like diffuse Na plus ions into the like some region of like initial region of the silicon oxide. So these Na plus ions are mobile in this region, but in the bulk, it is not like it cannot go through the bulk. So it is the, we call it as a Na plus diffused SiO2, and this is pure SiO2. And this is the monolayer MOS2, and on the top of monolayer MOS2, we have this drain source electrodes. So like if you, and this kind of ions, these are very like these are temperature sensitive, so we can increase the device conductance and decrease the device conductance by using also a temperature. So if we like see this graph, like so it demonstrates like at nearly room temperature, like less than room temperature, you will see a clockwise hysteresis behavior. And this clockwise hysteresis, like there is a some hysteresis like from back to forth and forth to back. So this small hysteresis is because of trapping of like, because this SiO2 is not like it is a 3D material, and when you like you have 2D material, on the 3D material it has some dangling bonds. So these dangling bonds can hold some electrons during the trace back. So this is the, and this hysteresis is coming because of this trapping. And but if you see at room temperature, like it's completely overlapping the back and forth. But if you see here, like there is a difference between this sweep and this sweep. So this is a counterclockwise direction. So if we sweep from minus 50 to plus 50 voltage, so it will like the black curve is the first sweep. Then while sweeping back, it increases the conductance. And here, if we go on increasing on the temperature, the memory window is also increased. So we have not gone very far away because we have to test the device like for number of attempts. So we just stop around 425 Kelvin. And here you can see there is a huge memory window. And while like this is the forward direction, and in this forward direction, like from this, when you like go in the backward direction current using this transport characteristics, so you see a increment in the conductance states. So this is because of this Na plus movement of Na plus ions towards the channel at the positive gate voltage, which actually additionally dopes our 2D materials, so that the conductance of the 2D materials or the Fermi level is rising. And also, and the vice versa is happening if we go to the negative gate voltage. So you are just moving away the Na plus ions from the 2D material, so it will decrease the conductance of the 2D material. So by using this concept, we can uh, demonstrate a single bit, 1-bit memory cell, where this is a pulse voltage that we give. So in this pulse voltage, positive 40 pulse is program and a negative 40 pulse is, let's say, erase voltage, and we read it at 0 gate voltage. So as you see, so this red and black, these like this circle and triangle and square. So these are actually like the average of the conductance value taken from this region. So after the programming, so during the programming of the memory, so this is the current, which is around 10 to the power minus 6. But after, like if you go to the read state after the programming, the current increases to 10 to the power like minus 7, let's say. So then after the erasing, you can see the current is like you get back to the original state. So like this, you switch between two different read state. So these are actually two different read state, and these are program state, and this is the erase state. So similarly, if you use a multiple number of pulses like 1 1, like this is a 2-bit logic, you can say 1 1 0 1 1 0 0 0. So you can, and this is the retention measurements taken after giving this kind of pulses. So you will see, you can see like 4 different memory like conductance states we can achieve using this like playing with pulses. And we can also realize 6-bit storage by using different pulsing of different pulsing with different amplitudes. So these are the 64 conductance states that we get throughout the from the picoampere region to a few orders of microampere regions, and these are the retention measurements. And like these are looking, this looks close, but like when you zoom it, but you can see like there is a no states are overlapping with each other. So this is a complete demonstration of 64 states on a single device. So, and using these different multi-bit memory states, so we simulate this neural network simulation. We use this MNIST dataset as our input. Then what we see is that like by using this multiple states, so the software, like our device, which is the blue one, which is after some repetitions, after some training, so it can perfectly like 98% recognize that it's a 9. So this is the confusion matrix that tell like we have also done it like using different digits like from 0 to 9. So, and you can see this diagonal matrix means, so this is the desired and this is the input. So this diagonal matrix like indicates like then our device can recognize the numbers or patterns. So, and I'm happy to say that like this ionotronic work is the kind of like a new model that we propose, and for that, like during the Nobel Prize in Physics collection, so our article is also like highlighted in this collection during the Nobel Prize announcement in 2024, which is to artificial intelligence. So basically, to conclude, so we fabricate the materials like using different approaches, and we make devices which can replicate some neuron and synapse behaviors. And we are trying to make it to communicate with the suitable algorithm and artificial neural networks, so that we develop a full system level. And other than that, we are like also working on this moire kind of material, that is just twisting between two different 2D materials that can generate different potentials for electrons, and these different potentials can be explored to uh, realize different multi-bit states. And the advantage is that you can get this kind of for one operation you can get like very low energy you can consume using this kind of architecture. And also we are trying to realize this as CMOS compatible neuromorphic devices, and somehow like use the spin of the electrons to generate some kind of neuromorphic systems. And I acknowledge my group, which is Sarosh Das, and also like my collaborators, Timur and Satyaprakash, and all of my lab mates. Yeah, thank you.
Thank you so much for this very nice presentation, new concepts, new ideas, new materials. I don't know if there are any questions from the audience. Please raise your hands, and I will give you the floor. Okay,
Yeah.
please ask a question. Um,
Yes.
when you try to make these graphene nanoribbons devices, okay,
Yes.
have you observed any gap, energy gap appears?
No, because like we didn't do any RPS measurements in these kind of structures.
Mhm.
But it is a
Be-
good like thing to see whether there is a gap or not. But these are not graphene nanoribbons. These are WH2 nanoribbons.
Okay, okay.
Okay.
WS2. Okay, okay.
Okay.
So, is there any let's say any progress how to make how to realize a continuous TMD film? For graphene, we have solved more or less the problem. We can have graphene at very large areas, okay? Although there are
Yes. Yes.
some grain boundaries, etc. Is there any progress with TMDs? Can we
Yes.
have
Yes. Yes.
real? Yeah.
People have a from China, they like this Fudan University.
Mhm,
They are actually they have synthesized a 12 this 2D TMD
mhm,
on a 12-inch wafer. So yeah, and also like in Penn State also people are doing using MOCVD technique. So the technique is metal oxide CVD,
mhm.
chemical vapor deposition. So
Yes.
by using that technique, you will get, yeah, of course there will be a grain boundaries. This is not as completely single crystals, but you will have a like graphene, you will have a like wafer scale growth.
Okay. Thank you. Um, any other question from the audience? Okay, so let me ask a very last question. Um,
Yes.
what about the field effect with the boron nitride? Have you tried any memory
Yes,
device
yes,
with?
yes. Actually, yeah, like if you use boron nitride, yeah, as a gate dielectric for these field effect transistors, so the thing is that it's the dielectric constant is not that much of high. So in that aspect, there are two aspects. The dielectric constant aspect. So you cannot use a very high we cannot give a very high electric field. using, because it will break. So because that's why people use 2D boron nitride as a memristor also, because it leakages, because of this leakage. But the like in other aspect, like if we integrate this with the 2D materials, the interface is very clean. So and because of this clean interface, you will get a very good transistor also. So there are two aspects, and the people are also like doing the developments to like to increase the transistor performance using HBN as a gate dielectric. Yeah. Thank you.
Okay. Okay. Let's see if there is any question in the chat.
Okay.
Okay. If not, I would like to thank you again, okay, for this nice
Okay.
presentation. Okay. Thank you so
Okay.
much.
Thank you. Thank you.
And I think it's time to move to the next presentation. I see that Rizil is already here. Okay, so the floor is yours, Rizil.
Okay, thank you.
Welcome.
And I am trying to share my screen, and one moment.
Yeah.
I don't see a version where I can share my entire desk.
In the center, in the bottom line.
Okay,
In the
found.
Yep.
Yes. Okay, I hope now it's visible, right?
Yes.
Okay.
Perfect. Thank you.
Okay, so hi everyone. So my name is Rijal Thomas, and I'm from Amo Kembe. So we are situated in Aachen. We are a research institute, foundry, a research foundry. And thank you, INFRACHIP, for giving me the platform to discuss some details that we did in the deep topic of neuromorphics. And we were working in this particular project. We were actually having two good partners, Fraunhofer in Berlin and ID Photonics. So just a small introduction to my company. We are a high-tech SME situated at Aachen, as I said before. And our managing director is Professor Max Lemme, who also holds a chair in the Aachen RWTH University. So we have a clean room of around 400 meters square with approximately 90 staff members. Our specialty lies in different domains, spanning from nanoelectronics, 2D materials, graphene, sensors, etc. And we started as a pure CMOS foundry, silicon-based. But then next we span to different exploring different materials like graphene, perovskites. We have a perovskite team now, and we do photonics, and we explore different exotic materials with quantum dots and etc. So you can get access to our technology. Like, we are the bridge between the fundamental research, which is being mainly carried by our university counterpart, but we don't do mass production as well. So we are trying to identify key commercializable projects, and then generate ideas and prototype. And basically, R&D is our product. So we work with publicly funded research projects and contract research, and we also do provide a small scale customer service as well. So as you all know, since we are also taking part in INFRACHIP, our technology is accessible to others. So we hold a 6-inch, mainly 6-inch, similar to CMOS line, spanning from deposition lithography. We have dry etching tools, and several characterization required for wafer scale. Also flexible with sample scale processes and prototype development. So you can find what technology offerings in our websites. Yeah. So that's it. Coming to the topic of today, which is neuromorphic computing. So I just realized the topic is vast. It starts from artificial intelligence, machine learning, to brain-inspired computing, and which is coming to my topic. I'm from nanophotonics team in Amokembe, so photonic neuromorphic computing, and that too, that's so it's a subset of subset of subset. So the field is very large. To give some basic market trends, we have this scale up of technology starting from few years back. We know 5 nanometer CMOS technology has been started by as a volume production. Then we went on to 3 nanometer CMOS technology, and now we are at the 2 nanometer. So pushing the limits of the technology of or physics. So basically, IMEC and TSMC and Samsung all leads or try with along many others are trying to push the frontiers of this technology. But this famous bottleneck of Moore's law. So this particular graph was taken from a book from Ines Darrell by Ines Darrell and Roy Rubenstein. So it's about fueling the next generation revolution of silicon photonics. So as you can see in the graph that over the past years, always the Moore's law has been obeying, and the scaling feature size has been going down, and then the number of transistors for every dollar we spend to buy a mobile phone or any electronic piece of electronic chip, the amount of transistors that contains in that one unit piece, and the value for $1, it has also been scaling up, but after a certain point, you see the plateau. It has started plateauing. So people are still pursuing technology from 5 to 3 to 2, but to scale past this Moore's law, it is really a challenge. So effort still continues, but the benefits of scaling, the speed, efficiency, cost, have seen some a hurdle there. So we have hit a break there. It is still being pursued, but then as I said, there's a limitation there. So this basically the ITRS, the International Technology Roadmap of Semiconductors, they are like a guiding body to assess the current market technology and giving guidelines and future prospects of it, which are the promising technology. So when we hit the limit of technology, we need to look at new technology. So uh, currently, a few of these technologies that under their radar, and they are guiding, watching for the main semiconductor big players to follow this. Obviously, the whole the hot topics, quantum computing, the 3-5 materials with heterogeneous and heterogeneous integration, neurosynaptic computing, which is a neuromorphic, and much others, including silicon photonics. So that's why this recently we have seen an explosion in such a topic, and which is also driven by small SMEs like us, and also big players like TSMC, Global Foundries, IMEC, and everyone. So looking at some review papers, some where people have compiled all these technologies together in one page. So around in 2012, there is a convolution neural network based demonstration called AlexNet, and recently up until 800 by NVIDIA. So these kind of new demonstration, these kind of new hardware accelerators has revolutionized this industry standards of computing, along with explosion of data. So which means which is very obvious that AI workloads as going up. It is going up. So mainly we need a huge demand. There exists a huge sub demand of energy, basically, which needs for supply power and cooling. And most of this current energy requirements are coming from this data centers, because they are the ones who handle all our data and distribute the data. So some of the recent metrics or the surveys show that the global electric consumption has gone up to hundreds of, it spans from 100 to around 600 terawatt hour. It's energy consumption which matches like a whole size electricity demands of whole size countries, something of the size of Sweden and Germany, etc. So we need something new to keep this under control. So hence that field of neuromorphic engineering. So it is a humble attempt to move elements of this machine learning and artificial intelligence into the hardware. So all the previous speakers have highlighted the importance of comparing to our brain, so which is very power efficient of few single or double digits, around 20 watts of power, which is being used by brain. That's the number being said by many people. And how does the brain work? So we are good at identifying uh, patterns, so which has kept alive for decades, centuries and millennia. Uh, so if you look at certain actions, like picking up a glass of water, so you don't first your brain has to identify the glass. First, you have to identify the glass with the water, and then your hand has to coordinate with it. So it's all a classified set. So it is not, even though it is being learned individually, step by step. We learn to categorize. We found the pattern, and then and just it is classified. The whole lifting process is just one single step classified under some certain set of actions. Even if you look at we are good at identifying patterns, right? So we look at constellations. So that's how we keep track of the skies and everything. But sometimes we overdo it. So I bet at least half of you have seen as a child, when you're a child, you used to spot patterns in clouds. So sometimes we overdo it when it's even not useful. But yeah, so that's the inherent nature of human brain. So what is brain doing exactly? At the same time, we don't want to make an exact copy of brain, because our brain is not well equipped to handle huge amounts of structured data and computations and everything. So we need to bridge the gap. So we need to be inspired from the brain, how the small power levels, how this much of unstructured data are being handled, and apply the same to the technology that the currently is being developed. So it's a gap. So it's none of them is a substitute for one another. So if you look at the trends survey that is being spotted here, you can see the NVIDIA and the Tensor, the Graphene Core, the Graph Core, Silicon Photonics, everything which covers this digital electronics. If when you plot the efficiency versus the computation density lies in the one corner. And then to push forward, silicon photonics was one of the early pioneer attempts, and now we are going for even nanophotonics and photonic neuromorphic, which has which promises energy, much more energy efficiency, up to 2 to 3 orders of magnitude higher. At the same time, for the computation density. Also on the left side, if you look at the graph here, these metrics are spotted with tops tera operations per second per millimeter square, 50 peta operations. So tera to peta is around 3 orders of magnitude higher. So there's clearly a distinction between electronics and photonics. Although these photonic parts, many of them are not like a full neuromorphic developed chip, but these numbers that we see here, around 50 pops per millimeter square. These are estimates based on few structures. So these structures which can handle huge amount of data in parallel. So there are some metrics. So people, when demonstrate some photonic structures, they just extrapolate this capability, where if you build it into a big system or big circuit. So we have to compare, to put into perspective of some measurement metrics. I mean, there are tons of measurement metrics. It's very hard to pin down a single metric, but just randomly picking some of them. Like if you take NVIDIA's A100, which is one of the most recently hot architecture developed in the industry. So they are doing billions of dense MAC operations. It's great for modern AI models. So, but these are not brain chips. They are not neuromorphic. They are traditional electronic CMOS circuits, but with much greater energy efficiency. So the energy operations, the energy consumption is said to be around few picojoule per Mac operation, and their energy density is set in terms of teraops. At the same time, reason we have heard of Lohi and Lohi 1, 2, and True North from IBM, Intel. These are something like neuromorphic chip. So they are trying to emulate synaptic operations of neurons. So they also consume in a similar range, maybe a bit higher, like in the order of 20 to few tens of picojoules per synaptic operation. But they are not measured in TOPS, but they are measured in terms of spiking operations, so which is more closer to the brain-like functionality. So, but this many electronic, when you talk about electronic neuromorphic architectures, they suffer from they are hugely interconnected. So electronics, when you scale up the interconnections, it reaches a wall because there are lots of crosstalks, and to actually address this in huge connectivity problem, what they people have tried is to do time division multiplexing. So when you do time division multiplexing, you're actually compromising on the bandwidth. So with by addressing this to specifications, that's how you can optimize this architecture. But just after pinning down this few specifications of electronics, if you look at photonics, obviously, it has tremendous bandwidth because of the high speed and everything. So it has a huge capability of multiplexing, both wavelengths and noise. So photons, when you put together in one fiber, they don't interact unless they are of specific phase and frequency. So if that's not the case, they just ignore each other and just go away. So the same principle can be used to actually pack dense amount of information in one fiber there. So that's one of the reasons we are current is being able to enjoy huge data, high speed internet, and with huge bandwidth and stuff. So yeah, as I said, they are immune to electromagnetic interference. And then if you design it properly, if you design your material properly, you have lower attenuation, and then they generate less heat if it's just optics. So yeah, this changes when you actually try to bring in electro-optic or other components, non-photonic components to the chip. So yes, we have possibility of co-integration with microelectronics, which is a good thing. And as I said before, and in the previous slide, I've showed photonic processes has around from tera to peta, 1 to 3 orders of magnitude improvement in efficiency and computation density. But where does photonics suffer? It's from this, this artificial networks. We put this non-linearity as of one important factor. So even though many of these photonic components may be able to provide some nonlinearity, the magnitude of the nonlinearity may not be that great. But if you want to apply a nonlinearity of a neuron through photon, you have to bring in some extra elements like some electronic components. Then again, we are reaching the bottleneck of bringing electronics into the chip. So there are certain options of doing like implementing weights and activation functions using something like a saturated absorber. So if you put some absorbing material on top of it, so the power actually, if it absorbs after a certain power, you see a plateauing, and then you can have this nonlinearity. Also, if you there are amplifiers like EDFA. So these are gain materials that you in the telecom industry you generally apply this EDFA to actually amplify the signals in between. So these are also have some nonlinear gain, so you can actually maybe utilize that. You can use photodiodes again. It's an electro-optic component. Photodiodes have both linear and nonlinear regime depending on where you operate operate the device on. So these are some possibilities how to implement neuronal nonlinearities in a photonic chip. So also same, there are some energy and latency bottlenecks when it comes to modulation and detection and everything. Because when you talk about modulation detection, again you're bringing electro-optic components. So we have to be careful about that. And then in electronics, you usually talk about bit precision. So in photonics, it's hard to say bit precision. It's mostly how much based on signal to noise ratio. So how much the output power of how much power in the optical amplitude of the output can be separated. So this also determined by the SNR. So when you want to have high SNR, you have to actually pump it with more power and more supply. Then again, that's bringing down the efficiency. So these are some negatives of photonics. So we need the best of all the worlds. We need tight integration of both photonics and electronics. So uh, again, people have been talking about memristive, which is great, which is a great addition to the neuromorphic community. Just because of all the three talks, I know you are aware of, you have much more details and insight into the memristive devices than me. So, but when you compare both of them, there are certain aspects where photonics lag. There are certain aspects memristor lags. For example, uh, exactly the speed. Memristor, the dynamics is based on this ion migration, which is a bit more slower than the photonics. So the speed scale of memristor, if I'm not wrong, it should be in picoseconds or higher. But photonics can go even lower side of picoseconds and even up to femtoseconds. But one thing photonics lacks is the memory. You cannot pin down a photon, you cannot store photon. So there is a problem of memory efficiency. But then people have come up with optical memristive optical memristive devices like GST and stuff. So these are phase change materials which can change their state in different levels of amorphous to crystalline state in different levels, not just 1 and 0, but in between different states. So depending on the power of the light it sees. So it can retain. So it can, if it sees some amount of some particular light, it can some particular photon, it can actually change the state, and based on the state, it means that it retains some level of memory. So we have several materials that is suitable for pure photonics memristor, and then which we can integrate. So out of these two, I think ITU and GST are one of the recently demonstrated in at least in a lab environment, in R&D environment, they have demonstrated foundry compatible processes. But again the scalability and the reliability. So if you want to do this optical switching, it needs to have, it needs to be the reliability of this much so and so cycles need to be tested. So these things are still in a very primitive state. But another one interesting component is graphene. So graphene recently, I mean, not recently, has been there for many years, but then it has, in my opinion, it has advanced a bit more than the rest. And recently we have a spin-off from AMO. It's called Black Semiconductors, and they are setting up a lab here in nearby Aachen itself. So they are creating a 8-inch, 6-inch or 8-inch foundry wafer scale processes with graphene-based devices. So so such devices are getting a bit more attention and hiring up the TRL level, technology readiness level. So now coming a bit more into photonics, again here lots of people are exploring on different architectures, photonic accelerator devices with MZI meshes. MZI meshes is just nothing. It's just two waveguides. When coming close together, they can interact, and they can, based on how close they are and how long they are, they can share. I mean, one photon will tunnel couple from one waveguide to another, so we can control the ratio of splitting. And then on if they are on two different arms, you can with some extra electro-optic components, you can actually control the phase and make them mix again and causing interference. So this kind of optical this kind of electro-optical component that we place there actually can be used as weights in a training. So when you build a very large mesh with it, and then you scale for each arms, you can place different electro-optic components, multiple electrode components, and it can be the most traditional way is to place a heater. So when you heat the material, uh, sorry, when you heat the material, the index of the waveguide changes, and then if the index of the waveguide changes, the speed, the phase the speed of the light changes, which means there is a delay in phase. The phase accumulates, and then they create a pattern. So this is a tiny component, but then they can be used for if you build a mesh like that, you can use it for MVM matrix vector multiplication operations. So we have photonic reservoirs, so which I will go into next step. So we have spiking neural network inspired architectures. We have PCM based architectures. We have combination of both. So if you look at this, for example, particular example here, so when the light enters here inside a micro ring resonator, so if it couples in the resonator, it can stay there for longer. And then you have multiple resonators here, and it is very sensitive to heat as well. So if you couple in more power based on the temperature of the chip and the power it sees, it can deviate from the stable position. And then when you put an extra signal into it, so based on the current state of the micro resonator, so you can have different levels of perturbation into this. So if starting from here to here, so it creates a pseudo memory. So from here to here, the previous signals retains its states inside the ring for certain time. So for reservoir computing, we have to understand whether are we approaching the brain inspired computing, whether from top to bottom or bottom to top. So like one approach from bottom to top is, as you said, so modeling a single neuron and then scaling it up. Or we have this other classical approaches where you don't care about single working of neuron, but you see them as holistically like a learning module. So when you look at the current architectures like recurrent neural networks and everything, it is one of the most widely used architectures. And then we have a special subset of recurrent neural network, which is reservoir. So in the recurrent neural network, you have to train each and every weights between the interconnected neurons. So it has been said it is a bit challenging to if it is a feed-forward network, it is a bit more simpler. But when it's recurrent networks, when it is fully back connected and everything, it is a bit more challenging to train each and every weight. But then it is reservoir is even a simplified model of recurrent neural networks, where you don't have to train the inside set at all. So this is a reservoir. You have many node and interconnected nodes in between. So you have a certain input, and then you let freely mix inside. So and then just take the output and you train at the output. So the training part is just very simplified just to the output readout section alone. So as I said, it's a subset of RNN, and it's very relatively easy than RNN, but at the same time retaining some specific properties of RNN. It can be fully passive, but it depends. Again, it depends on your design. People have showed fully passive as well as putting active elements into it. If it is fully passive, it means it is this block alone does not take in energy. All the energy consumption comes from either on the left or the right side of this block. So what it does on a very simplistic scale, it takes data. Like if like people see when you put in it, for example, if you put data into an XY plane, you see something like this. But if you rotate it something like this, you can see actually hyperplane separating this data. So it's a very simplistic visualization of how this kind of architectures work on this data by transforming this data into a higher plane and looking for separations for the classifications to happen. So if this kind of transformation happens within the reservoir, and then pass it to a next level of a simple neural network, some machine AI ML based a neural network, it can actually work it much more easily than feeding the data directly into the neural network. So this is what we've been working on. Specific example that is inspired from Professor Beansman group in Ghent University. So we have this edge node. It's an edge data center, and the data coming from here these goes through this optical reservoir architecture, and then finally we take the data which is coming from we don't do anything inside it. We leave it completely to freely mix inside as a passive network, and then take the data, detect at this output side, and do a simple training. And then what we did, we just did a smart network monitoring in the telecom network, which is a modulation format identification. So this is the chip that we made, and this is everything else is a test structures. The actual reservoir is only what you see here. So it is a single-digit millimeters size chip. And then photonic reservoir, we can make it random. We can it's up to us. We can decide it falls upon the designer, but it's fixed. So once you make a passive circuit there, you don't touch it. It's both a pro and con, because it's not adaptable to other or some other applications if you want, but that's another problem. So we let the light mix freely inside, and then just train on the output bits here. So at the moment we did it in this particular example, we did it in a digital network, but we can also bring the whole thing on the chip also. So this PC, the work that is done on a PC can be done on the chip also later. For this particular application, modulation format, even though this data, the data that we use is 32 gigabaud, but for specific applications that's shown here, we just need low speed photodiodes. So just I think it was 100 megahertz, so just kind of a very cheap photodiode. So what happens is we pass single the bits, the optical signals through optical fibers coming in terms of bits, one high and low, and then it enters the optical reservoir, and it enters each node. So here we are showing only one node as an example, but you can decide which nodes you want to input signal into, and at each node the signal travels through the delay lines, the orange lines. It's a waveguide, and then it goes to the next node and just keeps splitting. So as soon as you see the splitting, uh, you can see that power is actually being divided. So it goes more and more faint. So the more you keep the signal inside, it keeps mixing within itself, and then it also mixes with the pass signal. So it has certain short-term pseudo memory. So depending on the loss of the circuit so we did design, you actually maintain the signal inside the chip. So the more you retain the signal inside the reservoir circuit, the more you can make it mix inside, and then more rich features that you can actually extract from this. So in this our particular application, we used the 32 gigabaud, which translate to around 31 picoseconds. And then based on this symbol duration, so this is the duration of one symbol, so one data symbol, and based on this symbol, to which ratio you want to design, you can actually design your length of the data line. So so people have worked with different ratios, and different based on different applications, different ratios seem to have been working good for them. So generally, it falls in within a few millimeters, or it can be even a few hundreds of micrometers as well. So on a silicon SOI platform, we have made this chip. We have mainly waveguides. We have multimode interference couplers, MMIs, and then you cannot avoid waveguide crossings also. So if you look at this, all the nodes, we have this input and output. These are called grating couplers. Those are familiar with photonics will know it. So we couple light through these nodes and extract the light through this node, same nodes itself. So you have different nodes in the reservoir to actually put in the signal and take out the signal. So the choice of where to put and take out, it's yours. Yeah, it's a process of optimization. So, but if you want to package with the fiber array, like you have 16 inputs, 16 outputs, it's a very cumbersome. You cannot put the circuit is such a small. You cannot have all the inputs and all the outputs, all the fibers you cannot put at 16 positions on the chip. So we have to route out the the inputs and outputs at the two sides. I'll show in the next slide. I'll show how it is done. So when you route out the signals, so if you want the output here, and then when you route out the signal, you have to actually cross the lines there. So in electronics, you cannot do that. So you cannot cross one line over the other, it will cross talk. But in photonics, it's exactly the same reason which I told before, the photons won't interfere with each other. If designed properly, the photon coming from one will straightly go to 4, and it doesn't care what photon, if any photon comes from 2 to 3 or 3 to 2. So you can, if it designed properly, it will be with minimal crosstalk, and then you can smoothly guide the light from this location to the output that we need. So this is how the structures look inside when you look at under SEM. So these are the delay lines, which, so based on the length that you decide from one node to another, you can make it bigger or smaller. And then at each node, the light reaches each node, and it's a 3 by 3 MMI. So at any nodes, there are 3 output nodes. There are 3 input nodes, and there are 3 output nodes. So these MMIs, these nodes are designed in such a way that in whichever nodes the light comes, it will divide equally into 3 output ports. So meaning that it can go this way. So for example, if the light reaches this node from anywhere, it is either from the input or one of the two interconnect delays within the chip itself. The light will be equally distributed to here this way, or out, or one of them is output. So if you you're allowing the signal, a part of the signal, to roam freely inside the chip, and then giving it possible to mix with the next incoming signal. So we call it this as a 4x4 4-port architecture. So 4x4 means four nodes, 4x4 nodes here, and we have hyper arrays connected 16. We have 16 channels at input and output. It's a passive silicon reservoir with no active elements at the moment. And then the waveguide loss can be the loss from the waveguide. We have an intrinsic unit called dB per centimeter, but generally it tends to be in this range. But what happened with us when we fabricated a chip, we found out the waveguide loss was a bit high in our case. So we can, how to find the waveguide loss? We have our test structures, which I showed at the peripherals of the reservoir. We don't need it after testing. But you put the light in one grating coupler. So the grating couplers are the means of coupling in and out of the chip. You design some different waveguides of different length, and using a differential length method. So you look at the difference, and each difference, the output will differ based on the length. So the difference that coming from the unit length will give you the propagation loss of the waveguide. So this is an example of how we measure. So we are working at telecom wavelength, which is 1550 nanometer. So you can't see it, but this particular example that you see here is different. We work with telecom. We work with visible lights. We work with UV. So this is an just representative example to show what happens when you work with red light, when you work with blue light. So you input light into the chip, measure it from the output, and based on the power, you can see the power levels dropping for each length. And then for our particular chip, then when we looked at it, we found it was 6 dB per centimeter. So for 1 centimeter, you're losing around 6 dB, which is quite a lot and not so trivial. Maybe something has gone wrong, but 3 dB itself means 50%. So 6 dB means 25%. So this is, in terms of photonics language, is kind of high power. But what we thought, okay, wait a minute, why just throw it? Let's measure it. Let's apply and see what it gives. So we put this chip, we package this chip, and if you package this chip, it looks like this. And we implemented this in a full transceiver system. We have a transmitter. We did some modulation. We generated some data. So we were working on different modulation formats. Then we transmitted it. Then we put it in our chip, and then read out at the end. So this is a full system of schematic of a system, a transceiver system that we implement with help of HHI and IDP. And the performance that we saw was a bit surprising. But in spite of this high loss, the figure and the graph represent the same thing. So back to back means 0 kilometers. So these distances come in between the transmitter and the chip. So the more distance you have, the more fiber connection length you have, uh, the more dispersion the data goes through when traveling through the fiber. So up to 100 kilometers means you can connect from one data center to another data center. And 12 dB means very less noisy. 2 dB means it's highly noisy. So you can see when you increase the noise, the accuracy is dropping down, and we increase the distance, it's also dropping down. But then 2 dB is a very worst case scenario. I mean, according to our partners who did the experiment, they said typically they have it under 5 to 6 or 5 to 7 dB. 2 dB is like pushing the limits and seeing what this can do. And even 100 kilometers, you can see this classification task that we did it with this chip, and that too with a very highly lossy chip was impressive. This is at first we thought there's something wrong, but we did again and again. We fabricated more chips. We fabricate chips with even better losses, but even better losses doesn't make sense because already it is performing at higher limit. So we need a more complicated task. So uh, fabricating with better losses doesn't make sense here, but the message was clear. Even with such a high loss and a worst case performing scenario, this task of modulation moment identification was done well with this reservoir chip. And the confusion, and this is a confusion matrix. Confusion matrix is it's a complicated term for just a classification. So it says for if you these are the modulation formats that we use. It's either called quadrature amplitude modulation. So it's 4 quant, 16 quant, 32, and 64. So if you input 4 quant, how much of it is identified as 4 quant? That is 100%. If any misclassification happened, it comes here like this. So if you input 4 quant and how much of it is identified as a 4 quant, which is 60%, how much is identified as 32 quant, which is 30%. So this is misclassification. But this is again the worst case scenario of confusion matrix. Yeah. So so this might be suitable for the task as well. So which we are currently trying to explore. We are trying to look into some other tasks and to see to push the limits of this such a chip. But see what's happening. Is the chip actually doing anything, or is it that actually the neural network at the end which is helping us? So what we did, we totally removed the chip. We bypassed the chip and just connected the transmitter to, which is the normal scenario. We have a transmitter, we have a transmission link through optical fiber, and then we connect to the readout section. So which this time corresponded to only at 25% of classification accuracy. So 25% means it's just random guessing. So we have 4 things to choose from, and if we get 25%, that means it's random guessing. So what we did, we even we try to deepen the neural network architecture, but again, it still was 25%, which means that either this neural network architecture is not suitable for this task, or the complexity of neural network is simply not enough to perform this task. But then with the neuropic, we're able to get away with just one hidden layer, which means it is like a complementing this particular chip was complementing the neural network that we implement at the readout. So we looked also, I mean, the chip, we cannot vary the losses as we wish. So we can only hope to get the best loss when we fabricate something. So it's just accidental that we got a 6 dB per cm loss, which is high loss. But then all the other chips that we later measured was even better than that. But then if we just, by simulation, we just try to sweep the loss parameter and see how the accuracy goes. So even you can see up to 10 dB per cm, which is like even for the lossy chip. Even then, for certain scenarios, it is still within 95%. And then if you put the limits to the certain parameters in the which people in the telecom language will understand, which is not important here. But then even when you put it with the simulation wise, you can see that it is not dropping quite well. But if you look at this evolution of this prediction accuracy with different epochs is like a cycle of training. So you can see it is a bit different for each one, but again, at the end, if you give enough time, if you give enough learning, it will reach a decently good value. So this particular is our measurement that I showed before, which is 6 dB per cm, and then the rest of them is simulation. So in summary, it works well for high waveguide losses, and then but the good again surprising thing is there is something extra in the real chip, so which we were not actually able to identify in the simulation. Because in all scenarios, even when in some certain parameter variations, it's even more challenging. When it goes smaller, it means it's more challenging. So even challenging situations in the real chip was actually stayed at 100% all the time, which is still a real mystery for us still now. So this shows a schematic of the photonic reservoir, and then we want to check how the data complexity lies. So can we find some metrics to show that if the chip is performing well? So for that we collect the data. The n represents the length of the data. You can vary as much as you want, but then we have 16 outputs. So when they structured it was 16 by n array. And then there is a tool called PCA. So PCA is to actually look at the principal components. So it's like looking at the different dimensionality of the data. So when you compare this different dimensionality of the data, so the number of principal components on the x-axis denotes to how much components, components we were able to actually reduce the data. The data that is coming from the simulated pic uh, could be said that it has only 6 components or 6 dimensions, but at the same time, from the experimental pic may have 10 components. So something is extra in the actual pic, which again, as I said, it's something that we are looking into. But the message is it is actually very tolerant and very robust design. So if you put a pic into a very complicated task, and it was able to perform with 100% or high accuracy almost all the time. So even we've pushed this into a next level. So we have the certain modes in certain polarization in the fiber channel. We have TE and TM. So we implemented a polarization scrambler, which means it randomly scrambles polarization between X and Y, and then it rotates the polarization of the light. And then we changed from previously it was a coherent receiver. Coherent receiver is typically a very expensive tool, which is used for high-speed modulation, high-speed detection. But here we used a self-made PCB with a very low-speed photodiodes with some demultiplexing. And then it was found that we had to increase from 1 layer to 2 layer, but then even with this extra complexity with polarized scrambler and with low speed extra photodiodes without a coherent receiver, all the input the accuracy was still sufficiently high. And then we changed different input powers of the light. So so also, as I said before, if you allow the signals to freely mix inside for longer time, you will have better mixing, better rich interferences as a signal, which means rich features are being created, which can be extracted for the neural network. But if you reduce the input power, the signal attenuates even a bit more faster. So that's exactly what is seen here. So for higher power, you see it is always saturated, but for lower power, you can see for lower training, it is not yet saturated, but given enough time, it saturates to almost 100%. So 100 epochs is a typical training time we usually give for everyone for almost all our tasks. So again, people are free to choose between different epochs. It all depends on the training of overfitting or underfitting. So that's again other parameter to optimize on. So to summarize this, I want to emphasize it's quite obvious there is no single technology which lays the golden egg all the time. We need co-integration. So which is very clear. But in now we so on now photonics, from the perspective of photonic sky, we were actually exploring a photonic chip, which is much starting with very simple photonic passive photonic reservoir chip, which we found it is using all the standard silicon photonic component, which is not at all a very complex designs. Such a reservoir was performing with almost 100% accuracy across different scenarios. So the key features of this kind of such a reservoir is there's a good mixing of signal inside with its own past. So there is some short-term pseudo memory. We can actually do wavelength division multiplexing, as I said, different wavelengths, so information can be packed together. So increasing the computation density of such a PIC. And the digital readout was fairly simple for this particular task, but then we are looking into more even more challenging task at the moment, which means the accuracy might fall, but then again we're just trying to push the limits of such a device. So next thing we are looking into some examples that we are currently considering is Poisson estimation and nonlinearity mitigation. We just kind of consider one of the few of the complex tasks in telecom industry. But there are certain limitations with such a design because you cannot scale up the device. It is a bit more prone to temperature, and certain limitations are still need to be addressed. But again, this is not a single substitute for everything. It is one suggestion for a complementary device to other memristors or neuromorphic electronic counterparts that other people are developing. So finally, I would like to thank my partners, which is Fraunhofer and ID Photonics. So they have helped us a great deal in performing some of the experiments. And then, so a majority chunk of this research was carried out with the help of BMBF. Now it is BMFTR funding, which is a German funding with this Celtic Next umbrella project. So the project was INFRACHIP, and now we are doing with Sustainable Advance. And a big thanks to all my photonic team members and my group leader. So yeah, so Enes is the guy who was actually working with me on this photonic developing this PIC, but the rest of the contributions of the rest of the members are also quite evident in all of our works. Yeah, so that's it.
Thank you so much, Rizil, for this very comprehensive, excellent presentation on the photonics. Very nice applications. So, are there any questions? Please raise your hands if there are any questions. Okay. So, Rizil, I have a question.
Yes.
Regarding the scalability of photonic ICs, you demonstrate in one of your slides that you can have up to 256 inputs. Yes, here.
Okay.
No, I think in the previous slides. How many inputs you can have in your neural network?
The number of inputs, I mean, it depends. I mean,
is there
so
any limitation? I mean, for the scalability of the photonic inputs?
Yes. So there are a few things to consider here. So here, what we have done is we were actually an off-chip splitter. So if you're using off-chip splitter, we have to use this much kind of input. So here 16, and if you want to make it 32, it's just you see it consumes almost this much. I don't know how much is this, around 5 millimeter. 10 millimeters, so it becomes 10 millimeters. So it cannot improve an order of magnitude. So it can maybe coming from go from 16 to 32 or 64. That's the maximum. But then there is a caveat. So which we can also we have on-chip splitters. So you can have just go with one input fiber, but on the chip itself, using this is a multi-mode interferometer, right? So you can actually make different on-chip splitters, and then you can scale up a bit more.
Okay, thank you. Please, from the audience, are there any other questions? Okay, let's see the questions in chat. The chat. Okay, I have another question, Rizil.
Mm-hmm.
For reservoir computing, everything is fine because the weights are undetermined. Okay, I mean are stochastic. Okay,
Mm-hmm.
but what about other neural networks where you can photonic neural networks where you have to specify, let's say, the photonic analog of the resistance. Okay, that you have in node. Let's say that you implement a neural network using memristors. Okay, uh,
Mm-hmm.
training of this network means that you change and you find the optimal resistance for each node. Okay.
Mm-hmm.
Now, in what is the equivalent in photonic neural networks? Uh, what is let's say that we have a photonic neural network. What is the parameter that you have to train in every node?
Okay, so there is something called MZI meshes. So this is like a unit cell of such a mesh. So this is something we can't there is not resistance equivalent. So what we can so if we want to perturbate the light, so in the electronics we can slow down the electrons, right? So that is a resistance. But in on photonics perspective, if you want to slow down light, we have to accumulate phase. So this is one example that I can quote you. So there are in this particular unit, you can put heaters. So metals like tungsten, titanium, or titanium nitride, you can put heaters on top of it, and then you need to electrically connect them and
Okay.
pass some current. So heating that material heats up the material inside the waveguide material, and then there is a phase change uh, inside the material, which means it will slow down the photons a bit, meaning there is a phase difference, and then that's what. So tuning, programming this weights of which voltage to apply to this heater, that is the training phase involved in such a analog.
So in fact, you train the phase modulation. Okay.
Yes.
Yeah. Okay. Okay. Excellent. Excellent. Very nice work. Thank you. Are there any questions? No, I cannot see any other questions. So let's thank all the speakers uh, that participate in this afternoon session of digital school on resistive random access memories, okay, and technologies. So thank you very much, all the participants, all the lecturers, and see you again very soon. So bye bye.
Bye.
Thank you so much, and it was a great session.
Thank you.
Bye, everybody. Thank you, Panagiotis. Bye bye.